Hello boys and girls. In this video, there's this German saying, shooting with cannons at birds, meaning you're kind of overusing your weapons, your tools to solve problems that don't really need them. That's what we're going to do in this video. We're going to use the SU2 Lie group and its action on coordinates. We're going to use the rotation that can be represented using these small complex SU2 matrices to compute the square of the norm of the velocity of set point, if you think of it as a trajectory. Very related to the videos I already did on the SU2 and Pauli matrices. Here I discussed how this spherical coordinates representation comes about, how the matrices in general can be used, these small SU2 2x2 complex matrices. And then I dedicated a video to the Pauli matrices, which are the small Hermitian matrices in which you can encode your coordinates. Okay, so what are we going to get at? So if you have the perfect intuition, if you already know how objects in spherical coordinates are going to turn out, then we are going to end up with something of that form, where we have here r's and some sine of thetas corresponding to the vectors tangent to the sphere as you see it here. I'm just mentioning it to give some context. We're not necessarily going to need this stuff, since we're just going to use the SU2 action. But the end result will look like something like that here. So here's a question on physics stack exchange. For some reason, I didn't really find a nice Wikipedia article to demonstrate the same formula. But if you have this kinetic energy defined as such, 1/2 times the mass, you can ignore that. But what is important is here the square of the norm of the coordinate, if you think of like a point in free space parameterized with one parameter t. And then if you change that to spherical coordinates, you get this thing, and this is what we are going to end up with as well, right? So it's an expression involving derivatives of the radial coordinate and the theta coordinate coming down the ball, and then the phi coordinate going around the ball, multiplied with certain factors, and these are going to pop up. There's going to be one matrix manipulation that I will not do explicitly in this video, because it involves trigonometric function, and this is tedious, but like straightforward half angle manipulations. But otherwise the whole way to this will be clear, and we are just going to use very strong-ish formulas, matrix calculus, and so on. Everything will be hidden until the end when this formula pops out, which is kind of pretty in a sense. The point of it is, of course, just getting to know how to work with these gadgets in general, in also different situations than this one-point particle situations. Okay, so before we get into it, just 2-3 theorems that we're going to use, which are related to matrix calculus. There is this very nice Wikipedia page which lists, it's very long, and it lists a bunch of formulas. In this video, we are going to need, we have just one parameter, so we can call it time, and we take the derivative with this with respect to that parameter of very generic objects, let's say matrices. And so if we go to the matrix by scalar identities section here, we are going to make use of the fact that if you have these matrices, whatever dimension, multiplied together, and you take the derivative, then these behave as you would expect it in with the product rule. And the important thing is, of course, U and V might not commute, and these matrices might also not commute, but that's the order in which you take the derivative. So again, this is a very nice site. I recommend that you save that somewhere, because there are some formulas which are not as easy to intuit or keep in your head. Okay, so we remind behind us, the product rule is just as you would expect it, just keeping the order and getting two terms from a product. There is this very nice formula which I really like. The derivative of the exponential map. Here, exponential map is very generally understood. Here you see a definition at the beginning of the section. Here's a very cute picture of Poincaré. And the formula that we need in a simplified version, actually, that is this thing. So if you take the derivative of e to the x, where x depends on t, then in general, this is that thing, where this expression here is, you know, small art x is just taking the commutator with x, and this thing is to be understood as a polynomial series, so a series expansion of the function 1 minus e to the power of minus z divided by z, right? This is just some infinite series that you can easily compute as infinite series because it just involves the exponential function. And if you plug in this linear map that is taking the commutator, then you get this formula. You know, it's might be a little bit surprising, of course, if yeah, I don't know, let's say if if the matrix X is just a 1 times 1 matrix, and this is just, you know, f of x, then of course, you know, the derivative of e to the power of f of x is just e to the power of f of x times the derivative of f. And so you see here with these matrices, which might depend on x, there comes this term, which basically is only then non-zero when the matrix X does not commute with the derivative of itself, right? So basically, if the growth of the matrix is not along the same axis, if you will, as the matrix itself. Okay, this is a nice formula. We are actually also just going to need the case where this also becomes trivial, and we are just going to really use the case where x of t is linear with t, and then you can basically ignore this whole term because all the adds are 0. So we are also the point of this whole rant is that we are also basically going to use the derivative of the exponential as you would expect it, and here's sort of the justification why that works. Okay. Finally, we are not going to use this formula, although it's also good to remember. But we are going to use a sort of non-derivative version of it. I will show you it in a second. It's an interesting formula how you can compute the derivative of the determinant in this sort of algebraic sense. This is sort of a chain rule for the determinant, and here the Etchingate matrix, we are just going to need it for 2x2 matrices, since we're working with Pauli matrices, since we're just working with the small SU2. And in that case, I'm sure there is the explicit formula. Oh, wait a minute. I go to the Etchingate site on Wikipedia, and here we see that you compute it like that. Basically, you transpose, you change some signs, and it behaves similar to the inversion, except the unit of this thing is the same, like as inverted matrix. So basically, to multiply this by, you invert the matrix and multiply it by the determinant, roughly speaking. So yeah, here's this formula. Here you see it, right, that the matrix Etchingate is defined in a way that if you multiply it with A, you get something central proportional to the identity matrix. And also in our cases, this will be always trivial essentially, because we are going to use the Pauli matrices, which are traceless. So the Etchingate is basically just a multiple of the matrix itself. Okay. So what I'm actually going to use is the following formula, which is also very nice and good to remember. Here we're already in the page that we're going to get through in this video. There's this nice formula. So for 2x2 matrices, this holds for these 2 dimensions. If you want to compute the determinant of a sum of things, then you can actually compute that by just computing the determinants of the individual parts plus some inner product term, some trace term, which looks like that. Okay, and there are these formulas for like however many matrices you want. If you take this by induction, you get that. Actually, I never found this formula anywhere. There are stack exchanges where you can find this formula, and from this formula you can get to this formula by an induction step, and so on and so forth. And I tested it out, and in this video I'm bold enough to write the formula out in general, although I didn't formally do the induction proof for that, but you can test it in Mathematica, let's say for the first 5 or 7 easily, and you get that it works out. So here's some code that you find in the file below, as always in the GIS below. By the way, subscribe to the channel and give it a like. So yeah, here's this general nice formula how to compute the determinant of a sum of matrices, but really we are only going to need them in the 1-2 case scenario, right? And so also, if here's this formula where there's the sum of 3 matrices, 3 2x2 matrices, and here's 2 2x2 matrices, but here you can of course apply then this thing. So that means that the determinant of a sum of 3 matrices is a sum of 3 determinants plus some inner product term. And I say inner product term, I could also say trace term, but this language is of course motivated by the fact that for these Hermitian matrices, as we discussed in the previous video, they behave like an inner product, and the determinant behaves like minus the norm and so on. Okay. Yeah, so here's also this stack exchange link to where this thing is proven, although you can also you can also verify this like by hand. This is also an explicit proof, if you will. Okay, so before we get into the bulk of the video will be an application of the matrix calculus rules to very quickly end up with the kinetic energy term. I step through a bunch of things that are already discussed also in the previous video, right? In the video I dedicated an hour to just Pauli matrices to give you a nice overview of notation and facts and some classical applications. Again, in this video I have listed the things that we need in this video, okay, just for completeness. So yeah, okay, we define unit vector in a 3-dimensional space, and then we define a general point depending on coordinates is given like that, where these EI are of course just the unit vectors in in one direction. They are orthogonal to each other, and this is in some given frame. We define this map P, we define this map H of P, which maps this point into a general traceless Hermitian, i.e. self-adjoint 2x2 matrix. And then this has a lot of nice properties. For example, if you compute the determinant of such a general matrix, then you get minus exactly the sum of the squares, and it's minus the norm of this point, right? Okay, and then we can define the Pauli matrices, right? They are just the map of the unit vector looking in x dimension of H is 0, 1, 1, 0, and see, this is exactly this matrix. And similarly for the other Pauli matrices, they can be defined like that. As I discussed in the last video, the y1 has a negative sign here if you're using this function anyway. And then there are also the generators of the SU2 Lie-algebra, which are just multiples. They are anti-self-adjoint. I have spoken about this in detail in the last 2 videos. So that doesn't I forgot the dollar signs around this thing. So yeah, let's not hurry ourselves too much. Oh no, I didn't forget the dollar signs. Why does that not compute? Marv RM. Very confusing. Marv Oh, I forget a bracket, that's why. Okay, so the facts, more and more facts. The determinants of those are all very simple, plus minus 1. You can do the calculation yourself. As I argued, the adjunct of those is very simple to compute, because for 2x2 matrices you just flip around and change some signs and so on and so forth. Okay. Then there are commutation relations for these polymatrices as well as for the SU2 Lie-algebra. They are just different by some scalar factor. And here the magic is that if you go cyclic with the indices, for example G1 commuted with C2 is 2C3, and of course the commutator here, these brackets always mean bracket from A comma B is A times B minus B times A. Okay. I have also another video on the axioms of the Lie-algebras, which describe them as derivatives, is what they also are. And then also from the last video, you get unitary matrices by taking the exponential, which you can define in various ways, for example, by the power series, to get these sort of matrices, which are like 2x2 matrices with trigonometric functions and exponential functions. And here you say for these particular, like these three axis directions, you get again a matrix which is in the Lie-algebra, which is just this sum with here some angles, and this matrix is G, and G0 is the unit matrix here, because if you take an element of the algebra and multiply it with itself, for example, if you take G3 to the power of 2, so G3 with itself, then you get some complex number times the unit matrix. And so since you know the commutation relations of the G's, you also know how to commute to use with each other by just using the commutation relations here. Okay, spherical coordinates. The general point, we want to write it on in terms of function r, theta, and var phi. Var phi is the same as the phi previously. It's just a var in the LaTeX. So get another symbol, but it's just a phi, which is r times a generic point on the 2-sphere. The generic point on the 2-sphere looks like so. We discussed this in the first video, why that is the case. If you plug this into the H map, you get this matrix, which is the point on the 2-sphere, encoded as a Hermitian matrix. Here's the graphic for that. Here's a graphic for yeah, I guess the one that you can use to derive this, which is what we did in the video on Monday or so. Okay, and then the last tool that we need is the adjoint action of any G. We will discuss the adjoint action here. What I want to point out immediately is that the adjoint action of these two matrices, basically this is this u theta corresponds to the rotation around the y-axis, rotating theta down here, and this u phi corresponds to the rotation in the xy plane. And if this is applied to the Hermitian matrix stemming from the z-axis unit vector, which is itself basically just the polymatrix number 3, then after you do that, you find that this is exactly this thing, right? So this is a theorem, also explained in the last video, that you get the point on the generic point on a unit sphere by these rotations, and it indeed works out that you can do it like that. Okay, so what is the adjoint action? Well, okay, in the previous video we discussed or introduced the adjoint action with the conjugate transpose. Here I go back a step, don't assume unitarity, and just speak in terms of the g to the power of -1, where with this particular convention that the -1 is on this side. So when you use unitary matrices, this reduces to GMG star, as we had it in the last video. This is given like so, just a multiplication with, in our case, this will be just 2x2 matrices. And as you can see here, the determinant is left invariant by this, because inside of the determinant, you can break the product of the matrices into, this is the same as the product of the determinants of the individual components. And then the determinant of the inverse is 1 over the determinant of the object itself. So the g's cancel out, and you see that the determinant doesn't actually depend on g. And then if you use the matrix calculus rules that went over in the page, how to take the derivative, well, this is just exactly this thing, right? Okay, this is just applying the formula. And we are going to restrict ourselves to the u's that we saw above, right? We are going to, our g's will be these matrices, which are these exponentiations of SU2 elements of 2x2 matrices. And if you take the derivative of x with respect to a function of t, or with function of the angle itself, then what happens is just that whatever you exponentiated pops out. So that's exactly this rule, and this is why I'm motivated. This is what I'm motivated in this, where I quickly browsed over the Wikipedia page on the derivative of the exponential map. Okay, so we are going to get the kinetic energy by getting the square of the norm of the velocity, and the norm is just a determinant. So we have to take the derivative of the generic point in R3, sorry, for browsing around here. The generic point, sorry, so the point P, right? And the hard part is, of course, the angle part. The radial part will be relatively simple, but we want to take the derivative of this thing, and we are going to do that by taking the derivative of that thing, right? So this is our M. This is what we are, what is acted upon by this adjoint action. And since this is just a fixed matrix, this is actually going to be 0. And for that reason, we are, as we have it in our situation, only need the case where M is constant, and which means that this term is just 0. So by that logic, using the exponential g's and this constant, we take the derivative of that thing, and we get this situation. The a pops out here. We can put the a on the left side because the a and the g commute, right? Here this a and this g commute by the fact that g is just a function of like a power series of a, and so we can have the a on this side, and this is 0, and here we get minus a, and this a pops out on this side, right, for our exponential g. So this is this, and using the commutator, we put this together, and we get that the derivative of this thing, if m is constant and g is the exponential, is exactly the commutator. You know, this was just putting together the products here. And yeah, similarly, if we have now two g's, as is the case with our situation, right, we have the product of these unitary matrices. I mean, you can do the same thing. You expand it out, and then you pick together terms, and what you get is that if you take look at the first derivatives, you take it like you. In our case, this is going to be the derivative of t of the term which has the phi. This is the first term, basically. Our a1 is going to be proportional to g1. And if you collect these terms, since it's on the outside, it behaves just as this here, okay? And then there's the second one, which is closer to the m. And again, you just use the product rule for the matrices and collect the terms, and then you get that this a thing is applied similar to how you could find the commutator here to the commutator there, okay? I mean, if that is not completely obvious to you, write down these two lines where you expand the product rule and collect terms together and find how that works out like that. Okay, and so then we are basically done. This is the last page. So now we are going to make use of these formulas and to derive the velocity. So we are interested in taking the derivative of a point on a general point, and the harder part is the one where we look at the point on the sphere, right? So we are going to compute the norm squared by computing the determinant, right? Sorry, so to go back, why the determinant is relevant here, because of this formula, right? Because our h looks like so, and then the determinant of that is exactly minus the p squared. And so we are interested in the determinant of h of s taking the derivative of. This is going to be the velocity on the sphere squared minus. Yeah, and doing that, we just now use the formula for s, because s is, as we've argued, I hope this browsing is not too annoying, s is, like h of s is exactly this thing. And of course there's the h map is in between the s and these Hermitian matrices, but the h map is just a linear map, right? It's just associating these particular components in the in this matrix, and if you can pull out a scalar number or whatnot, for example, from a point, and this is the same as pulling it out from the matrix. And so the derivative also goes through, so we can also do the switcheroo with the derivative, because the h map is just linear. So so taking h of s prime is the same as h of s, and that primed, and here, since h of s is this is the unit vector in the z direction turned around, we can apply this formula. And so here on this side, this is just what we started with. This is just hs, right? This is just the point rotated around. The generator a1 is g3, right? This is what we have here, right? Times 1/2, and so we're missing a derivative also of these angles. So that's what we see here. So this is the commutator, of course, is also linear. I just pulled out these factors here, and here, okay, also just direct application of the formula we have derived here. So this is this thing. Okay, so now we know that the minus the norm squared, which is proportional to the kinetic energy, is the determinant of that. To compute the determinant of this sum of a bunch of matrices, we are now going to use this formula that we had introduced at the beginning, where we said the determinant for 2x2 matrices of a sum of matrices is the same as the sum of determinants plus this this trace term, right? Okay, here's a note that these factors 1/2 exactly cancel with the 2's of the commutator. So if we go back and see the commutators here, they have this 2 here. This is what will cancel out once all the commutators are expanded. And the determinants of the individual terms above are the sums of product, as I just said. Oh, I'm making the points sort of in the wrong order as I have written them down here. Let me finish my remark on the determinant and trace formula above, right? So the point is here now that to compute the determinant of this thing, we want to compute first the determinants of the individual terms, and we want to worry about the trace term later. And the trace term will actually turn out to be 0, simply because most of the all of the generators are traceless, right? The only thing that could happen is that some matrix proportional to the unit matrix pops up, but that doesn't happen because here just commutators are involved, and a commutator is also traceless. I know I'm using a lot of like linear algebra theorems here, like I take them for granted and argue very quickly, but at least you get a shorter video out of that for this reason. You can also easily like turn most of the things, this very abstract, like the joint representation and so on, into one-liner mathematical calculations and verify these things in one go. Okay, so let me follow through with the text as I've written it down here though. Yeah, the determinants of the individual terms in the above sum must also all be sums of products of the matrix elements of H of S. Yeah, so you know here, all these terms, like nothing is hard about these terms except maybe for the HS itself. I mean, the computing determinants for these very simple Pauli matrices and generators is trivial because these matrices are trivial. They have determinants plus minus 1 and so on. But this HS is a little bit uglier. It looks like so, right? It has trigonometric functions in it. And it also has actually it's a little bit simpler than I thought. I had remembered that there are also half angles there, but actually these are this is maybe I should have done it even more explicitly here. But here I'm just arguing that whatever survives here by taking the determinant is just whatever trigonometric functions are part of this thing, right? Because here these matrices have just matrix coefficients plus minus 1 plus minus I and nothing else. So the only thing that can survive is sines and cosines of theta and phi. And then these terms that are here, right? But if you compute the determinant of this thing, and then we can pull out the scalar and square it, and we're done with that. Okay, so first for the second term. The second term, the determinant is also super easy to compute because the adjoint action leaves the determinant invariant, as we said, right? So it's just the determinant of this thing, but the determinant of this thing must be like plus minus 1 or something like that, because this is just a sigma 3 matrix. This is just a multiple of the sigma 2 matrix. The commutator is just 2 times sigma 1. The 2 cancels out, so this is just a determinant of sigma 1, which is 1 or minus 1. So this thing here, as I just argued, I mean, it's sort of clear, even if the symbols might be scary, it's clear that the determinant of this is just plus or minus 1, and this minus 1. Okay, so using those, we simplify a bunch of terms here. We get that kinetic energy, and we're only interested here in this thing. Using this formula is, and you know, here you have to believe me that these trace terms are really just that you have to understand that like I didn't do the calculation here explicitly, that no central term survives, that no unit matrix survives in these objects, or in, like, say it a little bit differently, that when you do these adjunct matrix computations, which amount just to multiplying with some scalar, and then multiply these matrices together, that no equal matrices are multiplied together in a way that in the end this trace term in the determinant formula is anything else than 0. So with anything I've just said, this where am I here? Yeah, this formula reduces to this formula because P is just R times H of S, and so we have derivative of that times this thing. You take the determinant of this is plus minus 1, so you have this term. This term is the one I've left untouched. This is this one, and the R that comes from the multiplication. No, sorry for being a little bit in a hurry here, but So here, that's here, you know, the P is R times the point. So H of P is R times H of S. This is what we are dealing with. This R is simple. It's just a product rule. So that's why you get the derivative of R here. And if you use the determinant formula, then you compute the individual determinants, and then you have to square everything because you're dealing with two matrices. Okay, and yeah, as argued, but not actually like proven, the trace term is 0, and this thing also a one-liner in Mathematica, but I don't want to actually unpack these matrices. You get something which is sines or cosines, obviously, and turns out the phi terms cancel out, and you're just left with minus sine squared. Eventually, you plug this in, so this is actually false. I thought there's actually half identity terms, but they are not. I have just plugged it into Mathematica and had it done the validation for me. So that's why I actually never saw it, because Mathematica just simplifies it, but it doesn't make sense that there's half terms. And with that, we're at the final formula, right? So was a sort of speed run, a lot of complicated terms, but basically, if there's anything you take from this, apart from that it works because it has to work, is that if you take the derivative of these rotated, like a joint action rotated objects, then you just end up with these cumulative terms. And then if you know the Lie-algebra, if you know that how these things commute, then you can really break this down a lot and end up with just a few simpler matrices. Obviously here, again, this is like firing with cannons at small birds, but once you get, like, let's say you do quantum field theory of some very large, I mean, bigger than two-dimensional anyway, Lie groups involved, and you have like Lie group valued, Lie-algebra valued gauge fields, and there this sort of commutator computations pop up, and then it's good to have some intuition and believe it that it works. But the fact that indeed here we had exactly the right things popping out. Although again, I want to like be clear that with the caveats that I didn't actually compute this thing, although you can, I mean, it's a one-liner in Mathematica, and I didn't prove that the trace term is 0, but it's not too surprising given the fact that most of the 2x2 matrices in the basis, apart from the unit matrix, have trace 0. Okay, so that concludes the abstract SU2 computations. What is left in this saga is that I go back and use the Runge-Kutta integration scheme to compute the animation for the spherical pendulum. So stay tuned for that. Peace out.